Welcome to the 13th lecture of module 5 of distillation operation. In this module, we are discussing distillation operation. Before going to this lecture, let us have brief recap on our previous lecture. In our previous lecture, we have mainly considered Ponchon and Savarid method for design of distillation column. In this method, as you know, we need not to have the assumptions as we had with the McCabe-Thiele method. Assumptions of constant molal overflow is not required. So, this considered enthalpy balance equation in addition to the material balance. So, the stages obtained using this method is basically the actual number of stages or the real stages. So, in this method we can obtain real stages. Now, in this lecture we will mainly focus on design of packed distillation column. So, under which we will first consider design based on individual mass transfer coefficient and second we will consider design based on overall mass transfer coefficient. So, let us start with distillation in packed hours. Distillation of a liquid mixture in packed hours is preferred. Now, let us start with distillation in packed hours. Distillation of a liquid mixture in a packed hour is preferred in the following cases. One is vacuum or low pressure operation. So, if we have vacuum or low pressure operation, then packed tower may be used. The second case is the low capacity of the feed, and third case small allowable pressure drop. If we need small allowable pressure drop, then we can use packed hours. And third one, if there is corrosive services like the system corrode the equipment and other parts of the column, then packed hours may be preferred. This is a typical packed distillation columns. A packed tower for distillation is essentially similar to the one used for gas absorption. However, the tower should be provided with a distributor for the feed at appropriate location. So, we should have distributor at the feed point. This is in addition to the distributor of the reflux at the top. So, you can see we have a reflux and also we need to provide the distributor here. Besides, a condenser over here and a reflux drum which is over here and a reboiler. So, this is the reflux drum and this is the reboiler. There are two methods for the determination of the height of the packing. One of them is from the height and number of transfer unit, as we have discussed in case of packed hours in absorption, and second method is based on the HETP, height equivalent to a theoretical plate. To derive the design equations for the calculation of the packed height based on HTG and NTG, that is height of transfer unit, gas phase transfer unit, and NTG is number of gas phase transfer unit, we need to refer to this figure. Now, we have two sections. Above the fit locations is the rectifying sections and below the feed location is the stripping section. Now, assumptions over here is constant molar overflow and specific interfacial area is A. So, unit of A is meter square per meter cube of packing. Gas and liquid flow rate G and L in kilomole per hour meter cube. Liquid and gas phase mass transfer coefficient Kx dash and Ky dash. Now, local flux at height Z from bottom of the packed section we can define by Na. So, now the total interfacial surface would be A into dz. So, if we consider a differential area dz, differential sections dz, the total interfacial surface would be A into dz, which is shown in equation 1. Now, quantity of component A in the vapor passing through the differential sections, these sections dz, would be dgy, which is shown in equation 2. Now, quantity of component A in the liquid passing through the differential section should be dl into x. So, which is shown in equation 3. Now, if we do the differential mass balance equation for component A in the vapor phase, we can write A into dz into Na would be equal to dgy, which is equal to G into dy, which is equal to Ky dash A into yi minus y into dz, which is equal to G dy. So, since G is constant, as we have considered constant molar overflow, so this we can write G into dy. Ky dash A is the individual mass transfer coefficient in the gas phase. Now, differential mass balance equation for component A in the liquid phase, we can write A dz into Na is equal to dlx, which is equal to L into dx. It is similar assumptions we have taken the equimolar overflow or constant molar overflow for gas and liquid. So, L is constant. So, in that case we will have L into dx. So, from here we can write Kx dash into A x minus xi into dz would be equal to L dx. So, which is shown in equation 5. Now, the transport of more volatile component occurs from the liquid to the vapor phase. Its concentration in the vapor phase as well as in the liquid phase increases with Z. Now, if we rearrange equation 4 and integration over the rectifying section, if we do, this is equation 4, and if we do the rearrangement and integration over the height, that is from 0 to Zr dz, this Zr is the height of the rectifying section, packing height, which is equal to integral yf to y2, yf is the concentration of the feed, to y2 G dy divided by Ky dash A into yi minus y. So, after integrations it would be Zr would be equal to G by Ky dash A integral yf to y2 dy by yi minus y. So, from here we can write this part is basically HTG and the other integral part is the NTG. So, which is shown in equation 6. Now, Zr is the packing height in the rectifying section and HTG is the height of the transfer unit and can be calculated if Ky dash A is known. NTG is the number of transfer unit and can be obtained by numerical or graphical evaluation of the integral. Interfacial vapor composition, that is yi, as we have done before in case of absorption, for a set of values of y, yf less than y less than y1 are required for the numerical integration. Now, vapor phase equations 4 as we have obtained Ky dash A yi minus y into dz is equal to G into dy. Liquid phase equations we have obtained Kx dash A x minus xi dz is equal to L into dx. From these two equations we can obtain minus Kx dash A divided by Ky dash A is equal to y minus yi divided by x minus xi. The equation for the operating line for the rectifying section can be written for a given reflux R. Then take a point x y on the operating line and draw a line of slope Kx dash A by Ky dash A. This line meets the equilibrium curve at xi yi. If the individual coefficient remain constant over a section, such line from different points on the operating line are parallel. So, if this ratio remains constant throughout, then we can draw the parallel line from the operating line on the equilibrium curve. Hence, for a set of points x y, corresponding interfacial concentrations, that is xi yi, required for the integration can be obtained. Similar design equations can be written for the height and the number of individual liquid phase transfer unit. So, for liquid phase we can write dz would be equal to L dx divided by Kx dash A into x minus xi, and then if we integrate 0 to Zr, dz would be equal to integral xf to x2 L dx divided by Kx dash A into x minus xi. Now, after integration the left hand side would be Zr, which is equal to L by Kx dash A integral xf to x2 dx by x minus xi. So, from here we can write Zr is equal to, this part is nothing but HTL, the height of liquid phase transfer unit, and this part is nothing but number of liquid phase transfer unit. So, from here we can calculate the height of the packing in the rectifying section based on the liquid phase. The packed height can also be determined using the overall coefficient, that is capital Kx A dash and capital Ky dash A. The design equations can be obtained by putting Na is equal to Ky dash into y star minus y in equation 4 and Na is equal to Kx dash x minus x star in equation 5. So, if we do that, we will obtain Z is equal to HTOG, that is G by capital K dash y A and integral yf to y2 dy by y star minus y. This part is nothing but the NTOG, and we can also write in terms of HTOL, that is HTOL is L by capital Kx dash A. We assume that height of overall transfer unit, that is HTOG and HTOL reasonably constant over the section. The number of overall gas phase or liquid phase transfer unit are to be determined by graphical integration, as we have done for the individual mass transfer coefficient. Corresponding to a point xy on the operating line, we can obtain y star is the ordinate of the point vertically above it on the equilibrium curve, and x star is the abscissa of a point on the equilibrium line horizontally left to xy. Thus, the values of y star for a set of values of y which is yf less than y less than yi can be obtained and NTOG can be evaluated graphically or numerically. Now, mass exchange between the vapor and the liquid phases in distillation is mostly controlled by the vapor phase resistance. Thus, for the sake of accuracy, it is advisable to calculate the packed height using gas phase coefficient. Following the procedure described earlier, it is possible to combine the height of individual transfer unit to obtain the height of an overall transfer unit. Thus, 1 by Ky capital Ky dash would be equal to 1 by Ky dash plus equal to 1 by small Ky dash plus m by small k x dash. Here capital Ky dash is the overall gas phase mass transfer coefficient and small ky dash is the individual gas phase mass transfer coefficient and small k x dash is the individual mass transfer coefficient in the liquid phase and m is the Henry's constant. Similarly, we can write in terms of the overall mass transfer coefficient based on the liquid phase. So, we can write 1 by capital K x dash would be equal to 1 by m small k y dash plus 1 by small k x dash. So, this is equation 10. Now, we can relate with the equation derived earlier. HTOG would be equal to HTG plus m g by L HTG, and similarly for the liquid phase we can write HTOL would be equal to HTL plus L by mg HTG. So, m equal to m dash equal to m double dash, which is the slope of the straight equilibrium curve. A similar procedure is to be used to determine the packing height for the stripping section. So, once we can get the packing height in the stripping section, considering the procedure we followed in the rectifying section, we can find out the total height of the packing required for a distillation operation. Let us consider an example to solve the packed tower problems. A feed containing 50 mole percent A and 50 mole percent B is fed into a packed distillation column at atmospheric pressure. The feed flow rate is 50 kilomole per hour. The diameter of the column is 0.5 meter. The overhead product is 96% A and the bottom is 4% A. The feed is a saturated liquid and a reflux ratio of 1.5 is used. Find the packing height required for this separation. Rectifying section individual volumetric mass transfer coefficient or Ky dash A is 300 kilomole per hour meter cube and Kx dash A is 200 kilomole per hour meter cube. Stripping section individual volumetric mass transfer coefficients are Ky dash A is 400 kilomole per hour meter cube and Kx dash A is 300 kilomole per hour meter cube. Equilibrium data is given in this table. Now, we need to find out the height of the packing required for this separation. So, the data which are given, the feed condition 50 mole percent A and 50 mole percent B. Feed flow rate 50 kilomole per hour. Diameter of the column which is 0.5 meter. Rectifying section volumetric mass transfer coefficient Ky dash A is 300 kilomole per hour meter cube and Kx dash A is 200 kilomole per hour meter cube. Stripping section Ky dash A is 400 kilomole per hour meter cube and Kx dash A is 300 kilomole per hour meter cube. The overhead product is equal to 96% A and bottom products 4% E. Reflux ratio given which is equal to 1.5. So, these are the parameters given, so we have listed them. Now, let us do the material balance. Overall material balance is F is equal to d plus w. F is given 50, which is equal to d plus w. Now, component balance on A, it would be F x f would be equal to d x d plus w x w. Now, if we put F, this 50 into 0.5 would be equal to 0.96 d plus 0.04 w. So, from here we can write (25) would be equal to 0.96 d plus 0.04 w. So, therefore, we can calculate by substituting the total material balance on these equations, we can get d is equal to 25 kilomole per hour and W is equal to 25 kmol per hour. Now, vapor at the top tray V would be equal to d into R plus 1. So, we can substitute d 25 into 1.5 plus 1, which is equal to 62.5 kmol per hour. Now, reflux rate, which is L naught would be equal to d into R. D is 25 into L naught into R is 1.5, which is equal to 37.5 kilomole per hour. So, V dash is 62.5 kilomole per hour and L dash would be equal to L plus F, which is 37.5 plus 50, which is equal to 87.5 kilomole per hour. Now, for the rectifying section, we can obtain the operating line equation. Rectifying section, if we know the operating line equation, which is y is equal to r by r plus 1 into x plus x d by r plus 1. So, if we substitute the values, it is 1.5 by 1.5 plus 1 into x plus 0.96 divided by 1.5 plus 1. So, this will give y is equal to 0.06 x plus 0.384. So, 0.384 is the intercept on the y axis. Similarly, for the stripping section, we can write y is equal to L dash by L dash minus W into x minus w by L dash minus w into x w. So, if we substitute, then it would be 87.5 divided by 87.5 minus 25 x minus 25 by 87.5 minus 25 into 0.04. So, this would give y is equal to 1.4 x minus 0.016. This is the stripping section operating line equation and this is the rectifying section operating line equation. So, we know the fit condition and we know this point over here. Once we draw the operating line for the rectifying section, we locate xd on the 45-degree diagonal, which is not shown over here. So, there will be a 45-degree diagonal over here. And once we locate this point with the intercept on the y axis, that is 0.384, we can draw the operating line for the rectifying section. And we know the fit condition, which is 50% A and 50% B. So, 0.5 is over here. If we and the fit condition is given, so we locate this point on the 45-degree diagonal, that is xf is equal to 0.5 and the fit condition is given is saturated liquid. So, the feed line slope, it will go vertically. So, from this point we draw a vertical line. So, this is the Q line or feed line. And we locate the intersection point and we know the starting point where the bottom conditions 0.04 and we join these 2 points to get the operating line for the rectifying section, for the stripping section. Now, what we need to do, we know the slope of the line, that is in the rectifying section, we know minus k x dash a divided by k y dash a, which is equal to 200 by 300, which is equal to minus 0.667. So, with this is the slope of the tie line and with this we can draw several point lines in the rectifying section starting from the point 0.96 over here. So, with 0.96 we can draw with this slope which will connect to the equilibrium line and we will obtain the value of yi, which is shown over here. So, accordingly with different points we can draw the parallel line. If slope does not change, then we can obtain the values of yi, that is the equilibrium concentration or interfacial concentration. Then once we know these points, we can calculate 1 by yi minus y from this table. So, we can obtain this value. Now, For the stripping section, we can obtain the slope of the line by minus k x dash a divided by minus k y dash a, which is equal to minus 300 divided by 400, which is equal to minus 0.75. So, similar to the rectifying section, for the stripping section we can also, from the operating line, we can draw several lines with this slope minus 0.75 and we can obtain this table. So, this is yi we can get from the equilibrium intersection between this line and the equilibrium line. So, at different points from the stripping section we can obtain the values of yi. So, then we can also similar way we can calculate y by yi minus y. So, this is for the stripping section. If we plot both the sections, whatever both tables which we have obtained earlier, like this table for the stripping section and this table is for the rectifying section. If we take this data and plot y by yi minus y versus y, so we will obtain this curve. Now, the integral for number of turns per unit can be obtained by graphically show the area under the curve in the rectifying section we can obtain from here. This is for the rectifying section, about 6.2 unit, and similarly from this point we have about stripping section is about 5.53 unit. So, once we obtain this, then we can calculate the height of the tower. As we know, the column diameter is 0.5 meter. So, we can calculate the cross sectional area of the tower is about 0.1963 meter square. Now, Hg in the rectifying section is equal to 62.5 divided by 300, which is about 0.208 meter. And stripping section, height of turns per unit in the stripping section is about 62.5 divided by 400. So, which is about 0.1562 meter. Now, the total packed height would be equal to the sum of the height of the two sections. So, that would be 0.208 HTG into NTG, that is 6.2 plus 0.1562 into 5.53 unit. So, this is much meter is the height of the tower and it would give about 2.15 meter. So, this way we can solve a packed distillation column problems for a particular separation, we can obtain the height of the tower. So, thank you for your patience hearing, and we will continue our discussion on distillation in the next class.